Today we're going through 2.1 on the mole in our Foundations in Chemistry unit, part 2. We're working on FC2, construct an understanding of the mole as a unit for measuring the amount of a substance. So we will learn what a mole is and how to use it, what a mole looks like, and what Avogadro's number is and how to use it. If we're just talking about a collection of terms, we know that 1 dozen donuts is 12 donuts, 1 ream of paper means 500 sheets, and 1 case is 24 cans. Well, what is 1 mole? 1 mole is a collection that contains the same number of particles as there are carbon atoms in 12 grams of carbon, or 6.02 times 10 to the 23 atoms of an element. This is Avogadro's number, and it's just another way to count things. So just like 1 dozen means 12, 1 mole means 6.02 times 10 to the 23. Just a much larger number. How big a mole is, I will post this video after lesson for you to take a look at. So another examples here, 1 pair we know is 2, 1 dozen, 12, 1 mole is 6.02 times 10 to the 23. Half a pair is 1, half a dozen is 6, and half a mole is just half of that 6.02 times 10 to the 23. So it is 3.01 times 10 to the 23. And how did this mole develop, or the mole develop? Based on an Italian chemist Amedeo Avogadro's study of gases in the 1800s, he found that when equal volumes of gases are at the same conditions of temperature and pressure, they had an identical number of molecules present. This number of molecules was the same regardless of the type of gas. So for an example, the value was the same for hydrogen, a light gas, and bromine, a heavy gas. And they found the number was 6.02 times 10 to the 23, which became known as Avogadro's number. We have a little meme here. I just met you, and this is crazy. 6.0221415 times 10 to the 23, but here's my number, so call me maybe. And that is a lovely picture of Avogadro right there. If we were to actually measure out what mole of something looks like, we have 1 mole of aspirin in a beaker right there. And then we have 1 mole of copper 2 chloride, 1 mole of iron 3 oxide, and 1 mole of water. So if you take a look, they all actually are very different amounts of substances. Just like if you had 6.02 times 10 to the 23 pieces of sand, like little particles of sand, that'd be like a really, like would be about the same size as maybe something like aspirin. But if you had 6.02 times 10 to the 23 dogs, you would have a lot of dogs. So they could take out different volumes or different amounts of space, because remember that 1 mole of something is just 6.02 times 10 to the 23 parts or molecules or dogs of something. So 1 mole of aspirin, aspirin's a bigger molecule, so it would take up a little bit more space than something like water, which is a much smaller molecule. It takes up less space. Or here, 1 mole of sulfur is 32 grams, 1 mole of potassium dichromate is 294 grams, and 1 mole of graphite is 12 grams. If we look at that, the graphite is a much smaller molecule. It only takes, if we counted up 6.02 times 10 to the 23 graphite molecules, it would be a much smaller amount than potassium dichromate is a bigger molecule. So it has a much bigger amount. And We often talk about the mole in terms of moles of atoms, and we use that word, atom, when we're talking about an element. Now, 1 mole of carbon, carbon's by itself, it's not a compound, it's not with any other element. 1 mole of carbon by itself is 6.02 times 10 to the 23 carbon atoms. 1 mole of sodium is 6.02 times 10 to the 23 sodium atoms, and 1 mole of gold is 6.02 times 10 to the 23 gold atoms. Remembering, we use this term atoms when we're talking about an element by itself, which is a little bit different than when we have a covalent compound. 1 mole of a covalent compound, we use the term molecules. We have 1 mole of carbon dioxide is 6.02 times 10 to the 23 carbon dioxide molecules, and 1 mole of water is 6.02 times 10 to the 23 water molecules. And then if we have an ionic compound, we use the term formula units. We have 1 mole of sodium chloride, which is an ionic compound, so we use the term 6.02 times 10 to the 23 sodium chloride formula units, or 1 mole of potassium sulfate is equal to 6.02 times 10 to the 23 potassium sulfate formula units. So again, really important, when we have an element by itself, we use the term atoms. When we have a covalent compound, we use the term molecules, and when we have an ionic compound, we use the term formula units. For a little bit of a chart, just a little more condensed. Again, 1 mole of aluminum. Aluminum is a singular element, it's by itself. We know we need to write it as 6.02 times 10 to the 23 aluminum atoms. Again, 1 mole of sulfur, sulfur's by itself, so we use the term 6.02 times 10 to the 23 sulfur atoms. 1 mole of water, water is a covalent compound, 2 nonmetals. We use 6.02 times 10 to the 23 water molecules. And 1 mole of sodium chloride. Sodium chloride is an ionic compound, so we use 6.02 times 10 to the 23 sodium chloride formula units. And 1 mole of vitamin C, which we see there is C6H8O6, which is a covalent compound. We use the term 6.02 times 10 to the 23 vitamin C molecules. So that Avogadro's number can be written as an equality and 2 conversion factors. Our equality is 1 mole is equal to 6.02 times 10 to the 23 particles. Our conversion factors are 6.02 times 10 to the 23 particles over 1 mole, and 1 mole over 6.02 times 10 to the 23 particles. Again, that term particles is just written because if we have a lone element, we would replace that word with atoms. If we had an ionic compound, we would replace that word with molecules. And if we had if we had an ionic compound, we'd replace the term with formula unit. Sorry about that. We would replace it with formula units. And if we had a covalent compound, we would use the term molecules here. And if you remember with conversion factors, we can write the conversion factors either way. It's just like when we talked about in the introductory unit, we had 1 kilometer over 1,000 meters, or we could use 1,000 meters over 1 kilometer. Just our ratio here, both terms are equal. We can write it as a conversion factor or a kind of a ratio there, where the top is equal to the bottom. Same thing as our conversion factors for Avogadro's number. If we're using Avogadro's number, we can convert moles of a substance to particles. In this example, how many copper atoms are in 0.5 moles of copper? We start with 0.5 moles of copper, and we use our conversion factor. So often you'll see me write this in brackets. And since we started with moles of copper need to go on the bottom, so we can cancel them out, which means we need to put 6.02 times 10 to the 23 copper atoms on top. And then we multiply the two numbers on top and divide it by the number on the bottom. So we go 0.50 moles times 6.02 times 10 to the 23, all divided by 1. We get 3.0 times 10 to the 23 copper atoms. And remember, we need to write that to proper significant figures. Well, the number in our question, we always look to that number in our question. It has 2 significant figures, so our answer must have 2 significant figures. Avogadro's number is a scientific standard. It's a number that we know scientifically, I guess. Whenever we have a number that's given to us as a standard, we don't need to take into account that number with scientific notation. So we don't look to Avogadro's number. We don't say, okay, well, that's 3 significant figures. Our answer, if our number in the question had 4 significant figures, Avogadro's number has 3. We wouldn't use that 3 significant figures to figure out what our final significant figures needs to be. We only ever use the numbers in our question. If we take a look at this next example, we can convert particles of a substance to moles. Our question is, how many moles of carbon dioxide are in 2.50 times 10 to the 24 molecules of carbon dioxide? We start with our number in the question, which is 2.50 times 10 to the 24 molecules. We write that out, and then we write out our conversion factor. And since we have molecules of carbon dioxide on top, we need to write molecules of carbon dioxide on the bottom. So those units cancel off, and we're left with the units that we want. Our units of moles is the units that we want. Because our question's asking, how many moles of carbon dioxide are there in that many molecules of carbon dioxide? So to figure out this answer on our calculators, we would have to go 2.50 times 10 to the 24 divided by 6.02 times 10 to the 23. Or you can think about it in terms of, sometimes it's helpful to write an equals sign, multiply everything on the top. You'd have 2.50 times 10 to the 24 on top, because you'd go that number times 1 and divide it by everything multiplied on the bottom, and then divide those two numbers. And our final answer is going to be 4.15 moles of carbon dioxide, which is the 3 significant figures because our number in our question has 3 significant figures. Making sure we remember that significant figures, we remember our units as well. And a couple learning checks here. The number of atoms in 2 moles of aluminum. So again, we start with 2 moles of aluminum in our question. We go, okay, 0.2 moles. And then we use our conversion factor to convert it to atoms. Since we have moles on top, we know we need moles on the bottom, which means Avogadro's number needs to go on top. And our moles will cancel off. We have to go 2 times 6.02 times 10 to the 23. And we come out with the answer C, 1.2 times 10 to the 24 aluminum atoms. If we'd like to do our second learning check here, the question asks the number of moles of sulfur in 1.8 times 10 to the 24 atoms of sulfur. If we start with our number in the question, And we need to use our conversion factor to convert to moles. We have atoms on top. We know we're going to need to write 6.02 times 10 to the 23 atoms on the bottom, which means moles need to go on top. Atoms cancels off then, and we get 2.99003. But when we look at our number in the question, it asks for, it has two significant figures. Our final answer is going to have to be two significant figures. So we look at the number before, which is a 9, which means we need to round up to 3. And we can't just leave it as 3, we have to write it as 3.0, or we don't have two significant figures. So 3.0 moles, which is B. Subscripts also play an important role when we're talking about moles. The subscripts in a formula give the relationship of atoms in the formula. The moles of each element is 1 mole of a compound. So when we're talking about glucose molecule here, in 1 molecule, or in 1 mole of glucose, we have 6 atoms of carbon, and 12 atoms of hydrogen, and 6 atoms of oxygen, as well as 6 moles of carbon, 12 moles of hydrogen, and 6 moles of oxygen. Just like saying in 1 human, like saying myself, I have 2 hands, right? So in 1 mole of me, let's say I have 1 mole of Shanna's, or Miss Van's. 1 mole of Miss Van's is 6.02 times 10 to the 23 Miss Van's, right? But if I talked about how many moles of hands do I have, it's twice as many moles of hands than if I had 6.02 times 10 to the 23 of me, right? Because every one of me has 2 hands. A little confusing there, but we'll get it. For our subscript state atoms and the moles, again, 1 mole of aspirin here has 9 moles of carbon, 8 moles of hydrogen, and 4 moles of oxygen. Right, so just again, if you have 1 mole of yourself, so if I had 1 mole of Miss Van's, that's 1 mole of me is 6.02 times 10 to the 23 mole, Miss Van's, I guess. And that's 1 mole of Miss Van's has 6.02 times 10 to the 23 Miss Van's. Now if I talked about how many hands I had, it'd be, I have 2 moles of hands. Which meant I'd have 2 times 6.02 times 10 to the 23 hands. And our subscripts are used for conversion factors to relate moles of each element in 1 mole of a compound. For aspirin, it can be written as for 9 moles of carbon, there's 1 mole of aspirin, 8 moles of hydrogen is 1 mole of aspirin, 4 moles of oxygen is 1 mole of aspirin, and vice versa, right? Remember that you can always flip these factors, conversion factors around either way, and write them either way, depending on what number you're starting with in the question. A guide to calculating the particles of a substance. Step 1 will determine the number of moles. We write a plan to convert the moles to atoms or molecules. Use Avogadro's number to write conversion factors and set up a problem to convert given moles to atoms or molecules. If we took a look at this example here, how many oxygen atoms are in 0.150 moles of aspirin? So we always start with the number in our question. We start with 0.150 moles. of aspirin. And if we take a look, for every 1 mole of aspirin, so every 1 aspirin contains 4 moles or 4 oxygen. So for every 1 mole of aspirin, we have 4 oxygens, or 4 moles of oxygen. And if we look, that cancels off, right? So I wrote aspirin on the bottom because I wanted aspirin to cancel off with aspirin on the top. And we want to be left with moles of oxygen. And then we know we need to convert it to atoms because this question isn't asking us how many moles of oxygen we have. It's asking us how many oxygen atoms. And whenever we want oxygen atoms, we know we're going to need to use 6.02 times 10 to the 23 atoms per mole. So since we have moles on the top, we want to write moles on the bottom, and 6.02 times 10 to the 23 atoms on the top. If we take a look now, moles cancels off, and we're left with just atoms. And if we work that all out, we are going to get 3.61 times 10 to the 23 oxygen atoms.